And this is static equilibrium. And the classic problem is one in which an object is hung from two cables. And you are asked to find the tension, the force in cable A, cable B, both of them, and perhaps even the weight of the mass. In this case, you're asked to find the tension in cables A and B. And if we pull this out here, the key point is that the mass is in static equilibrium. That implies and means that the sum of all forces acting on it have to equal zero. It's not moving. Therefore, the sum of the forces is equal to zero. First thing you should do when you do one of these problems is to draw the free body diagram. And if I start this up, you can see the sum of the forces is equal to 0, and you can see the two components, the x component of the A vector and the x component of the B vector there, they have to equal 0. Okay, you add those two vectors together. And the vectors of the y components of vectors A and B, and then if I take away the original vectors representing the cables, you can see what's left are just the components. And that kind of simplifies the image a little bit for you. So you can see that the x components have to equal 0. And then the y components have to equal 0. So the tension in the cables, the y components of both of those cables, has to be equal and opposite to the weight of the object, which is vector C. I want to caution you on what vector C represents. It represents the weight of the object. You're not always going to be given the mass like in this problem. Sometimes you're going to get the weight. And you'll know the difference because weight is expressed in newtons because it's a force, and mass is typically in kilograms. So be careful about that. Don't be tripped up by that. So once you have the free body diagram drawn, you have to write out the sum of the forces in the x and y direction statements or equations. This is exactly what we've been doing with finding the net external force and finding the resultant during the beginning of the year. However, in this case, we know that the sum of them is going to be equal to 0 because the object is in static equilibrium. It's not moving, so the forces have to equal 0. So I've got it laid out here. And I'm going to click here under the A, and that's the x component of vector A. It's flashing on the free body diagram in the corner as well as in the equation, so you can see it. And we have to subtract the x component of vector B. Again, look at the free body diagram and the equation. For vector C, there isn't an x component. It's one vector on the y-axis, so that is 0, and that's equal to 0. Now let's do the sum of the forces in the y direction. We'll take the y component of vector A, and there we have it. And we're going to add that the y component of vector B, and there you see that. And I wonder if we have to add or subtract vector C. That lies entirely on the y-axis. If you're thinking subtracting, that's correct because it is in the negative y direction, and that is the weight. So that is mass times gravity. And we set that all equal to 0. Notice we have two equations and two unknowns. So there is a way to solve this. And that is by making a substitution from one equation into the other. Easiest way to get the answer here is to solve for A or B in the first equation. And that's what I do. I move B cosine 40 to the other side of the equal sign. I then solve for A. And at this point, it's suggested that you go ahead and calculate cosine 40 divided by cosine 60. And that gives us a value for A, which is 1.532b. We're going to go ahead and substitute this value for A into the equation below. And I show here by the arrows and then the box that A, which is 1.532b, the 1.532b has been substituted for A in that equation. It's inside the box. I've also moved mg to the other side. So we're going to go ahead and solve for b now. That is the only variable in this equation. First step is to factor out that b, make things a little bit easier, and then calculate the terms inside the parentheses, as well as now is a good time to put the value for the weight, mass times gravity, in. And this is what we get. So solving for b, you get 59.7 newtons. Plugging that value back into the expression for A that we set up above, we find that the tension in cable A is 91.5 newtons. In this case, we were asked to find the tension in the two cables. Other questions will ask you to perhaps find the weight of the object and the tension in the cable, or merely the weight. A question might ask you for an angle. Whatever the question asks, you should draw a free body diagram and then write the sum of the forces in the x direction, make it equal to 0. Write the sum of the forces in the y direction, make those equal to 0. And at that point, as I'm fond of saying, you should see the path to salvation. You ought to be able to see what you need to do to get the answer that the question is looking for.